Okay, so today we are going to talk about the second derivative test. It is an alternative to the first derivative test for finding mins and maxes for a function. It is not to be confused, and it sometimes is, with using the second derivative to find concavity and points of inflection. So it tells me about mins and maxes, whereas, last week we worked on using the second derivative to find concavity and POIs. So what I want you to do first is find and justify any mins and maxes with the first derivative test for the function y equals x to the fourth minus 18x squared. And depending on when you are doing this, this may look familiar. So do the whole min at blank because blank, max at blank because blank, all that stuff to get to that. And hit pause, and I will have my answer show up. So hit pause, do it. Okay, here comes the answer. So we start with the function. We take its derivative. We then go and factor it. I get 4x and x squared minus 9. That's difference of two squares, so x minus 3 and x plus 3. That gives me three critical values, 0, and then plus or minus 3. Now, this is the spot where you can decide to use the second derivative test instead, right? So when I'm actually going to use this example to show you what the second derivative test is. When I do that, I'm going to use all this work right here. But if we're doing the first derivative test, which you already know, we take and we figure out what the signs are, where it's positive, where it's negative, and then we draw some arrows. Well, we have our intervals up here too. And then we make our statements. Min at x equals plus or minus 3, and it's fine to jam those into the same statement because y prime changes minus to plus, and max at x equals 0 right here because y prime changes plus to minus. So, what I want you to do now is look at this graph. I'm going to draw a graph for you. If I can get this to work. All right, I got boom, boom, boom. All right. Now I would like you to, in your mind, say where the POIs are. I'll take my mouse over it, and I just want you to say, there, we got a POI. And then same thing, tell me when to stop for the next one, right there. And then we'll go down. We can't really tell if there's one over here. What is the value of the second derivative? Actually, I'm not going to write it like that. I'm going to write y double prime equals, what do we know about y double prime in this whole range here? It's concave down. Y double prime is negative. What about here? We know y double prime is positive. And what do we know about here? Y double prime is negative. Now, I want you to next identify where there are mins and maxes on this graph. Well, we got one here, and we got one here, and we got one here. Let's draw the tangent line there. What do I know y prime is here? Well, the first derivative is 0. I should maybe back up a little bit. Our plan here is to use the second derivative to find mins and maxes. So I want to use concavity visually to say, oh, if I got this type of concave and this thing going on with the first derivative, then I know I'm going to get a max, or I know I'm going to get a min. So here, notice at my min, y prime is equal to 0 as well, and here at the max, y prime is equal to 0. What I want you to notice is that this is true here and here. I get my first derivative as 0 and my second derivative as negative. If I have concave down and I have a first derivative of 0, I have to have a max. Come over to the min here. What would I need to have to get the min? Let's do this. What do I need to get that min? Well, I need y prime equal to 0, and I need the second derivative to be positive, right? So that, if you think about it, oops. anytime I have a second derivative that's positive and a first derivative that's 0, I have to have that minimum. Same thing goes with this. I have to get a maximum. So that leads us to what the first derivative or the second derivative test says. I'll write it out. All right. If y, so this is the second, and you could write it in multiple different ways, but if y prime of a is equal to 0 and y double prime of a is negative, what I always like to do here is draw concave down so I don't mess it up, right? So the second derivative is negative, the first derivative is positive. What are we going to get? Then y has a max. The reason why I draw this every time when I have that negative first derivative is because in my mind, negative intuitively means minimum, right? But as you can see, the negative doesn't mean minimum. The negative means concave down, which paired with this being equal to 0 gives me a maximum, right? And then the second half of the second derivative test is if y double prime of, if y prime of a is 0, so if a function's flat, and y double prime of a is positive, so if it's flat and concave up, draw that concave up anytime you have that plus, then y has a min. And there's one more part to this. If y double prime of a, if y prime of a is 0, and, well, look, we got negative covered, we got positive covered. What other options could there be? Well, y double prime of a could be equal to 0. And then what's that mean? It means that the second derivative test is inconclusive. Usually there's a shoulder, something like this, when this takes place, but it is not like that in all scenarios, and I could come up with some counterexamples if I wanted to. I guess I should say it has a max at x equals a. At x equals a. So hopefully you are on board with that and you see that it happens in this visually. Now we're going to go ahead and apply that to this thing. So I'm going to pause for a moment. So we're going to do it with the same function that we did up top, right? This one right here. We should get mins at plus or minus 3 and then a max at 0. Remember, I said we do all this work, so I just copied and pasted that. And the new work that we're going to have is going to replace all of this right here. Usually, so I've got all this work finding the critical values. And now, the next step is to get the second derivative. Y double prime is equal to, well, it's 12x squared minus 36. Now, notice, y double prime of 0, well, that's negative 36, so it's negative, right? And then I can just turn, and I can turn this into my statement. Y double prime of 0 is negative, and y prime of 0 is 0. So, and I always draw concave down. Y has a max at x equals 0. Does that match up here? It does, right? And you see I didn't have to do all this chart stuff, which can be complicated and annoying, right? So come down here, I'll find y double prime of 3. Well, that is, look, it's 12 times 9 minus 36. Well, I know 12 times 9 is definitely a lot bigger than 36. So I'm just going to write positive. And then what I'm going to notice is that, oh, well, if I plug in -3 here, I'm just going to square and get that same 9, right? So my next line is going to be y double prime of plus or minus 3. Well, I can see that that's positive. And I'm going to turn it right into my statement. Y prime of plus or minus 3 is equal to 0. And then remember, positive second derivative, concave up. Okay, so y, has, what do we have there? A min at x equals plus or minus 3. Now, you may say when to use either one of these. Well, sometimes we have to do this test here because finding the second derivative is really complicated. But if the second derivative is easy to find, I almost use it all the time. It's just quicker. There's less work, and I like it a lot. So let's do one more example. Example 2. I can fit it in the time we have. Let's do y equals x to the 4th minus 4x cubed. All right, I want to use a second derivative test on this to find and justify any mins or maxes. So let's find the first derivative. 4x cubed minus 12x squared. I can pull an x squared out, and a 4 actually. X minus 3. So my CVs at x equals 0, 3. Now I find y double prime, so that's taking the derivative of this. That is equal to 12x squared minus 24x. And now I'm going to plug in my values. Y double prime of 0, I take this guy, is equal to 0. That means inconclusive. So I just move on. It's likely a shoulder. In fact, we could use the first derivative test to show that it's a shoulder in this case, I think. And then I'm going to find y double prime of, 3? Well, that's 12 times 3 squared is 9, minus 24 times 3. I have a trick here. I'm going to show you how to change what we have here, right? And do some basic math that maybe you don't know, maybe you think this way, but I usually give these kinds of tips in class. See that 24? That's really 12 times 2. Well, what I'm going to do is write this as 12 times 9 minus 12 times, and then I'm going to take this 2 and multiply it by that 3 to get 6. And then I got 12 times 9 minus 12 times 6. I really only need to know if this is positive or negative. Because 9 is bigger than 6, and the 9 has the positive term, this is positive, right? So I got the first derivative equal to 0, and the second derivative positive. So y double prime of 3 is positive. Draw concave up. And hold on, y prime of 3 is 0. So y has a min at x equals, what is it? 3. One thing I'll say is that this is sometimes a lot easier to do with trig functions, because a lot of times finding when a trig function is positive or negative is more complicated than dealing with this thing, right? Or than dealing with these guys and making this chart, right? So that might make it a lot easier for some of you to find and justify mins and maxes on trig functions. So you got another tool in the box to be able to figure out when you got mins and maxes, and you're going to go do some right now.